Swayam Prabha. Digital India. Educated India.
Welcome to Organic Chemistry Paper 3. In Unit 3, we are studying about heterocyclic compounds. In Lecture 5, we are going to study about reactions of 5-membered heterocycles. I am Dr. Balaji, currently working as Associate Professor in the School of Biotechnology at Jawaharlal Nehru University. This project is sponsored by DTH Swayam Prabha, MHRD, New Delhi. The topics that will be covered in this session include electrophilic substitution of 5-membered heterocycles. We are going to study about the basics of reactivity between benzene and 5-membered heterocycles, how they are related to each other. We will be studying about individual reactions like reactions of furan. We will study about electrophilic substitutions. Along with that, we will also study about Diels Alder reactions of furan, which is very unique. We will also be looking at how different non-aromatic products can be formed. So, these are all the two different types of reactions which we will be studying along with the electrophilic substitutions. And when we talk about reactions of Pyrrole, we will be studying about reactivity and regioselectivity, how these two are interrelated. We will also study about unique reactions of Pyrrole, which is a Mannich reaction. Then we will study about various electrophilic substitutions of Thiophene and how what are the different types of reagents that are generally used for this electrophilic substitution we will study. Then we will also look at a few examples of drug containing 5-membered heterocycles. Welcome to the session on reactions of 5-membered heterocycles. Let us look at a brief overview of electrophilic substitutions on heterocyclic compounds. So, basically we know aromatic systems, especially benzene and other pi-rich systems, can undergo electrophilic substitution very readily, and we have seen that 5-membered heterocycles, especially furan, thiophene and pyrrole, are also having aromatic characters. So, that means they also generally would like to undergo electrophilic substitution reaction similar to benzene. So, here we are going to compare the reactivity between benzene and 5-membered heterocycles with respect to electrophilic substitution reactions. If you look at the resonance energy, benzene is having a higher resonance energy compared to thiophene, furan or pyrrole. So, in other words, benzene is much more stable compared to thiophene, furan or pyrrole. In other words, what we can say is, if we speak in terms of reactivity, thiophene, furan and pyrrole can undergo reactions much better than benzene itself when we talk about electrophilic substitution reaction. So, in other words, what we can say is these compounds, these 5-membered heterocycles can undergo a very fast electrophilic substitution even under milder conditions compared to benzene. So, here are some of the various parameters based on which we can actually talk about this. The first one is the resonance energy. So, in the case of resonance energy, the 5-membered heterocycles have lower resonance energy, indicating that they are better substrate for electrophilic substitution. And there are various reactions which actually confirms this. For example, if you look at the nitration reaction, acetic anhydride and nitric acid at 0 degree centigrade is just sufficient to nitrate these 5-membered heterocycles. Whereas, when we talk about benzene required fuming sulfuric acid and nitric acid, that means highly concentrated conditions and required for conducting nitration on benzene. And when we talk about sulfonation, sulfur trioxide and pyridine at 0 degree centigrade is sufficient to sulfonate these 5-membered heterocycles, whereas benzene requires sulfuric acid and sulfur trioxide, especially the fuming sulfuric acid is required for sulfonation reaction. So, in other words, what we can say is the higher stability or the resonance energy of the benzene is responsible for the lower reactivity of electrophilic substitution compared to the 5-membered heterocycles. And similarly, halogenation occurs at 0 degree centigrade, whereas in the case of benzene, we do need a Lewis acid for effecting this reaction, and of course, we know various Lewis acids are available for effecting this particular reaction, and of course, we also need to heat that reaction to happen. And formylation, when we talk about there is no formylation reactions when DMF POCl3 is reacted to give the formyl derivative from benzene, whereas when we talk about the 5-membered heterocycles, DMF POCl3 readily gives a formylation product. And of course, Diels-Alder reaction, furan actually undergoes or forms the Diels-Alder adduct, but thiophene and Pyrrole are not. Similarly, benzene does not undergo Diels-Alder reaction. And when we talk about Friedel-Crafts alkylation, with the help of Lewis acid like AlCl3, zinc chloride, etc., Friedel-Crafts acylation and alkylations are possible in the case of benzene, whereas when we talk about furan, thiophene and Pyrrole, these reactions are highly fast. That's the reason they undergo polymerization in the case of alkylation, so it is of no use. And when we talk about acylation, it is possible to acylate heterocyclic compounds using Lewis acid conditions. So let us look at the reactivity of the heterocycle. We are going to talk about two things. That's what we saw earlier. When benzene is having a higher resonance energy, it is actually having lower reactivity towards electrophiles. And here we are going to consider the thermodynamic stability with kinetic reactivity. That means we are going to compare two major parameters. One is the thermodynamic factor, another one is the kinetic factor, because these are all the two factors which decide how a reaction actually proceeds. So when the stability is lower, the reactivity is going to be higher. And we have seen that heterocycles are having lower resonance energy than benzene, so here they are more reactive than benzene. And the presence of the heteroatom, especially with the lone pair, can release electron to stabilize the intermediate, thereby lowering the activation energy. So there are two ways by which the reaction actually proceeds in a much better way. The first one is there is no heteroatom present in benzene, so that means electrons cannot be released, especially the lone pair of electrons from nitrogen, oxygen or sulfur, which is present in the 5-membered heterocycle. And we also have earlier seen that these are called pi excessive rings, because the lone pair from the heteroatom can be given to the ring. That's the reason the ring becomes pi excessive. When there is pi excessive, that means there is more electron density, then electrophile can easily be attacked. So this is the reason these heterocycles are much more reactive, because there is a lowering of activation energy because the electrons are being released from the heteroatom to the ring. And one more important thing we have to talk about in the heterocycle is the orientation of the product formation, because we have two positions, we have two places in which the reaction can occur. One is at the 2 position, or sometimes called as the alpha substitution. Another one is at 3 position, or the beta substitution. So these can be explained very easily using resonance structures. We will be looking at how each position can undergo reaction. We will see. When we talk about the electrophilic substitution, as we have mentioned the last point, we are talking about the regioselectivity. So that means when the electrophile E plus attacks the heterocyclic ring, the electrophile can add to position number 2, or the electrophile can add to position number 3. So depending on the stability of the intermediate that is formed, we can say which product is going to be formed as the major one. When we compare the reactivity, Pyrrole is much more reactive compared to furan and thiophene, which all the three are much more reactive than benzene when we talk about electrophilic substitution reactions. And the thiophene is the most aromatic in nature or character, so that's the reason it undergoes the slowest reaction. This is what we have seen earlier also. When the resonance energy is higher, the reactivity is going to be lower. Since Pyrrole and furan are having lower resonance energy, they undergo reactions very effectively. In other words, they In other words, they undergo the reaction under very mild conditions. And when we talk about the orientation, the alpha substitution is favored over beta substitution because there are more resonance structures that can be drawn for the alpha substitution compared to beta substitution. And also the charge is less localized, that means it applies to the transition state. So these are all the reason by which the 2 substitution is the most favored one compared to 3 substitution. And of course, depending on what is the heteroatom, we can also have beta substitution or reaction occurring at the 3 position is observed. Say for example, when Pyrrole is reacted, when Pyrrole is nitrated in the presence of acetic anhydride and nitric acid, we get 4:1 ratio of the product. That means this 2 substituted product is formed in 4 and 3 substituted product is formed in 1 ratio. So that means we can say 80% to 20%. 80-20 ratio the products are formed. But when the heteroatom is oxygen, that means when the furan undergoes the same nitration reaction, the yields are 6:1. That means the ratio of the 2 substitution is much higher compared to the 3 substituted products. So this is how we can say the regioselectivity is different for different heterocycles. Let us start our reactions with the furan. So we will look at the first reaction, which is the sulfonation reaction. We have seen earlier that furan undergoes sulfonation in the presence of pyridine. When sulfur trioxide is reacted with furan in the presence of pyridine, we get 2,5-disulfonic acid derivative. And when the bromination occurs, especially in the solvent like a dioxane, we get the 2-bromo derivative. So as we have seen earlier in the nitration also, the furan prefers 2 substituted derivatives, and the nitration when we carry out in the presence of acetic anhydride and nitric acid, we end up with the 2 nitro derivatives. So the same reaction can also be performed with the nitronium fluoroborate. This also gives the 2 nitro derivative as the major product. And of course, there are other reactions. Acylation can be carried out in the presence of acetic anhydride. So when we use Lewis acid SnCl4, the reaction actually happens at the 2 positions or preferentially at the 2 position. But if the 2 positions are blocked, as in 2,5-dimethyl furan, then the only available position is the 3 position. So the acylation also occurs at 3 position, but here if you look at the temperature is little bit higher. In other words, what we can say is at 20 degree, or when there is no substitution, or if the 2 position is free, then the acylation preferentially takes at 2 position, and if the 2 position is blocked, the 3 position can also be acylated, but we require higher temperature for this reaction to occur. So as we have seen, heterocycles, the 5-membered heterocycle can very readily undergo formylation reaction with DMF and POCl3. So the introduction of the aldehyde group happens at the 2 position. So all this reaction says that the preferential reactivity of furan is at 2 position. And of course, this is one of the unique reactions of furan which is not shown by the other heterocycles. Furan undergoes Diels-Alder reaction because furan is having the least resonance energy of all the 3 heterocycles, especially between furan, thiophene and Pyrrole. Furan is having the lowest resonance energy, so it generally behaves like a diene. So that means furan can very readily undergo Diels-Alder reaction. So this is what is given here as examples. So the reaction with maleic anhydride as shown here gives both the exo product and the endo product. Here the endo product is a kinetic product which equilibrates to exo product, because when the thermodynamic products are formed, they are formed at a slower rate, but they are more stable. So if we give enough time for the reaction to proceed, then the most stable product, that is the exo product, is formed in this reaction. And similarly, we can also see other adducts which are being formed when furan undergoes Diels-Alder reaction. Of course, there is one another additional reaction which is also possible, is the retro-Diels-Alder reaction. So once the furan undergoes Diels-Alder reaction in the presence of an acid at high temperature, it can undergo ring opening to give a aromatic product. So if we look at, we are starting with the aromatic heterocycle, and this gives a non-aromatic, this is non-aromatic product, but this non-aromatic product on heating in the presence of acid undergoes rearrangement to give a aromatic product. So these reactions are highly possible reactions, because this formation of the aromatic system is the driving force for this retro Diels-Alder reaction. So a 5-membered furan can be converted to a 6-membered benzene derivative using Diels-Alder reaction. So there is also another case where the Diels-Alder reaction is shown here, because in this particular case this is a intramolecular reaction. So we have a double bond which is positioned suitably to undergo Diels-Alder reaction, but this is not an activated double bond. Even if it is not an activated double bond, this particular case the Diels-Alder reaction very readily occurs, because it is the intramolecular Diels-Alder reaction leading to the cyclic product. So this is a very unique reactivity of furan. One more important thing is, like we have seen in the case of Diels-Alder reaction, we are getting a non-aromatic product, but other than Diels-Alder reaction, even electrophilic reactions, some of the electrophilic reactions of furan can give non-aromatic products. Say for example, when we talk about the nitration reaction in the presence of methanol, so there are two possibilities. We are getting a carbocation that is formed when the electrophile, the nitronium ion, attacks the double bond. So we end up with a carbocation. So this carbocation can actually lose a proton. If this proton is lost, then we end up only with the nitration product. So that is the 2-nitration what we have seen is the final product that will be obtained if the loss of this particular hydrogen takes place. This is one type of reaction, but there is also another possibility that instead of this hydrogen is lost as a proton, what can happen is, like the double bond can be shifted here as shown here, and in this particular case the solvent actually donates, especially here the methoxide ion, that is the solvent, attacks this electrophilic carbon, that is the carbocation is being attacked by the OMe minus. The nucleophile that is present in this reaction can attack this carbon. That leads to the non-aromatic product. So this is also possible in the case of furan. So this is a very unique reaction, that is under the electrophilic condition the reaction actually occurs to give a non-aromatic product. So there is also another reaction in which bromine water or bromine in methanol that reacts with the furan to give a non-aromatic product. If it is a bromine water, we end up with a dibromo derivative, and if it is a bromine and methanol, we actually end up with a dimethoxide derivative. So in the case of bromine reaction, it is actually the initial step is the bromonium ion addition is the first one, and the second step is the bromide ion addition. So, the bromonium ion actually adds to this second position carbon to give the carbocation. We saw how this the double bond migration leads to a carbocation on this position, and once a carbocation is formed in this position, now the bromide ion, which is a nucleophile, attacks this to give the dibromo derivative. And when we talk about the same reaction in the presence of bromine and methanol, actually here the bromine is being replaced by the methanol, because methoxide ion, being a stronger nucleophile, displaces the bromine. So, that is the reason we end up with a dimethoxy derivative. So, these are all the examples of the non-aromatic product that can be formed during a electrophilic substitution reaction of furan. So, let us look at the resonance structures which are responsible for the observed regioselectivity. We have the heterocycle, and the electrophile now attacks the heterocycle. We have two positions at which the electrophile can attack. It can attack position 2 or it can attack at position 3. So, let us look at if the electrophile attacks at position 2. When the electrophile attacks at position 2, the double bond is polarized. So, that is the reason we end up with a carbocation on 3 position, and now this particular double bond can shift to stabilize this carbocation. So, we end up with a carbocation on position number 5. So, this is position number 2, this is position number 3, position number 4 and position number 5. So, first we have a carbocation at 3 position, then we have a carbocation at 5 position. Now, there is lone pair on this particular heteroatom. So, this can actually stabilize this neighboring carbocation. So, the heteroatom now has a positive charge. So, we actually have 3 different resonance structures possible when the electrophile attacks position number 2. And this one can actually lose a proton to give our final product as a 2 substituted one. And let us look at if the electrophile attacks the 3 position. So, how do we know whether it attacks 2 or 3 position? Because there is a double bond. So, when the double bond is there, both the position can be attacked by the electrophile. So, if it attacks the 3 position, then we have a carbocation at 2 position. Now, there is a lone pair on this heteroatom. So, this can be shifted here to stabilize the carbocation. So, we have a heteroatom having the positive charge, and 3 position is the place where the electrophile is added. So, in this particular case, we only have just 2 resonance structures to stabilize the intermediate. So, between 3 resonance structures for 2 substitution versus only 2 resonance structures for the 3 substitution actually tells that the reaction preferentially occurs at 2 position. In other words, the electrophilic substitution preferentially occurs at 2 position in the case of heterocycles, 5-membered heterocycles. So, let us compare the reactivity of all the 3 heteroatoms. First one is the thiophene, next furan and pyrrole. When we talk about all these 3 heterocycles, we have seen the regioselectivity of the electrophilic substitution. So, 2 position is the most preferred position for the electrophilic substitution for thiophene and furan. But in the case of pyrrole, we have both the 2 and 3 positions possible. And when we talk about the halogenation, thiophene and furan undergoes polyhalogenation. So, it is not a preferred reaction. And if you look at pyrrole, the presence of substituents on N affects the reactivity. We will see some examples how the presence of different substituents on the pyrrole nitrogen affects the reactivity. We will see. And with respect to the electrophilic substitution reaction, all the 3 reacts with electrophile. That means thiophene reacts with electrophile, but furan, when we look at this, reacts slower than pyrrole but faster than thiophene. So, this is one difference. So, if you look at the reactivity, thiophene is having the highest resonance energy. So, it is having the lowest reactivity with electrophile. Pyrrole is having the lowest resonance energy. So, this is much more reactive towards electrophiles than benzene, furan and thiophene. So, this is much more reactive than all the other aromatic systems, especially furan, thiophene and benzene. And when we look at furan is in between thiophene and pyrrole. So, this is the reactivity with respect to electrophiles, and one special reaction which we have seen for furan is due to the lower resonance energy, this actually behaves like a conjugated diene. So, this undergoes Diels-Alder reaction very readily. So, that is one of the major difference of reactivity between the three heterocycles. So, if you look at the reactivity of Pyrrole, Pyrrole is a secondary amine. We know that Pyrrole is a nitrogen, this is a secondary amine, but unfortunately this does not form adduct with methyl iodide. So, this is observation number 1. And the reaction with the pyrrole and acetic anhydride fails to give the corresponding amide, that means 1-acyl pyrrole, because whenever we have a amine, primary or secondary amine, let us say, if this is acylated, we end up with a acylation on nitrogen. So, we have the nitrogen. So, the acyl group is introduced. In other words, we form the amide. This is nothing but the amide. So, an amine can be converted to amide by the reaction with acyl chloride or acetic anhydride. But this reaction is a very specific for either primary amine or secondary amine. But pyrrole is a secondary amine, but that does not give this particular reaction. Now, we are going to look at why this is happening. So, if we look at pyrrole, when the electrophile, because many of the electrophilic reactions can happen on carbon or it can happen on also nitrogen. So, let us assume in the case of methyl iodide, so there is a methyl cation. So, this methyl cation is now going to attack either nitrogen or it can attack the carbon, because if it attacks the nitrogen, what we are going to end up is this particular product where nitrogen is having a positive charge. On the other hand, if it attacks the carbon, then we have more resonance structures that are possible. So, that is the reason basically the attack on carbon takes place very readily when we have a electrophile, and this is applicable even for the acylation reaction. So, for both alkylation and acylation reactions, if the alkyl group or the alkyl cation or the acyl cation, if it attacks the nitrogen, we do not have lots of resonance structures to stabilize that intermediate that is formed, whereas if the reaction occurs on the carbon, we have lots of, at least we have 3 resonance structures that can stabilize that intermediate. So, this is the driving force for the reaction to happen on carbon and not on nitrogen. So, this is the reason this nitrogen, that is the pyrrole nitrogen, does not behave like a secondary amine. So, as we have seen how we can control the reactivity of pyrrole system. So, depending on the substituent, when we have a substituent or we can actually have a 3 substitution. This is what we have seen earlier also, like the second position or the third position acylation or electrophilic substitutions are possible in pyrrole. So, here are a couple of examples which actually shows that this reaction actually occurs. So, acetic anhydride and AlCl3 in the presence of a base, the base is added at the second step. So, the first acylation in the presence of AlCl3 gives a product on 3 substitution. That means, this is nothing but the Friedel-Crafts reaction, and this Friedel-Crafts reaction generally produces a 3 substituted product if the R group is a SO2 pH group, and similarly if we have a silyl derivative, triisopropyl silyl group is present on nitrogen, the nitration also gives the 3 substituted product as the major one. So, this is how we can actually control the 3 substitution by the appropriate substitution on nitrogen. Although the second substitution is the most preferred reaction, by having different substitutions on the pyrrole nitrogen, we can actually direct the reaction towards the 3 position. So, this is also possible in the case of pyrrole. Now, the major question many people will have is like, is pyrrole an acid or a base? Because we have seen that the pyrrole does not behave like a typical secondary amine. So, does it mean is it behaves like a acid? So, if we look at the pyrrole to behave like an acid, so we know the structure of pyrrole. So, we have the N and H. So, according to our simple acid base theory, like what is an acid, what is a base, if you go back to the Arrhenius and the previous very old theories, what we talk about is anything that can give out a proton is called a acid. So, if we take HCl, if H plus can be formed very readily, then HCl is called a strong acid. Similar to that, in the case of pyrrole, if the pyrrole can actually give out a proton, then we can call pyrrole as an acid. And whether this reaction actually happens, if we look at this, basically if pyrrole hydrogen is removed by a strong base, we end up with a negative charge on nitrogen. So, the moment the negative charge is present on nitrogen, we can write various resonance structures. So, this tells that this hydrogen is going to be little bit more acidic and it can easily be removed, because the stabilizing resonance structures are the driving force for the proton to be lost. So, we can say that pyrrole behaves like an acid, and of course, it is shown that pyrrole is a weak, very weak acid. Its pKa is around 17.5. And of course, further confirmation to pyrrole an acid is given by the reactions with bases. When pyrrole is treated with potassium hydroxide, a strong base, what happens is like we form the corresponding salt, and now the nitrogen can be easily acylated or alkylated. So, we have seen earlier that pyrrole cannot be acylated or alkylated using any electrophilic reagent. The reason is like pyrrole basically gives the reaction on the C substitution, or carbon is the place where the reaction actually undergoes. That is the reason this does not behave like a secondary amine. But when the same pyrrole is treated with a strong base, then what happens is the hydrogen is replaced or hydrogen is removed. In other words, now this behaves like an acid. So, this particular anion can now undergo acylation very readily. That is the reason we end up with the acylated or alkylated derivatives. And similarly, when sodium hydride is treated with pyrrole, we actually get the sodium salt. So, these are all a couple of reactions which tells that pyrrole behaves like an acid. So, does it mean that pyrrole is not a base? Of course, we have some other reactions which tells that pyrrole can also behave like a very, very weak base. So, when the H3O plus is reacted with aromatic pyrrole, we end up with a non-aromatic product and water. So, in this particular reaction, we are ending when the acid, that is the H plus, is added to the nitrogen, we end up with a non-aromatic product. So, in this particular case, pyrrole is more basic compared to H3O plus or water, we can say. So, in this particular case, compared to water, pyrrole is a base. So, this is another way of explaining that pyrrole can behave like both acid and base. Let us look at some of the electrophilic reactions of pyrrole. We have earlier seen that the Wills-Mayer-Haag formulation reaction, which uses DMF and POCl3, gives or introduction of a aldehyde group. So, the formulation takes place on the 2 position, and when we use acetic anhydride and the nitric acid at minus 10 degrees centigrade, this is what we have seen in the beginning of our session, that 2 substitution and 3 substitution both happen like 80:20 ratio. So, this is another reaction in which 2 and 3 substitutions, that is the nitration, takes place. on Pyrrole, and treatment with the NBS actually gives the 2-bromo substitution. Treatment with bromine at 0 degree actually gives a tetrabromo derivative. This is what we have seen. The polybromination actually is happening in these kind of systems. And treatment with trifluoroacetic anhydride gives the 2 substituted acylated trifluoroacylated derivative. And pyridine and sulfonic acid gives the 2 substitution. So, in all the cases the 2 substitution happens very readily. In other words, the regioselectivity is always preferred towards 2 position. And there are also other reactions. When Pyrrole undergoes oxidation, we get carboxylic acid. If we start with Pyrrole aldehyde, this on oxidation gives a corresponding carboxylic acid, and reduction of this Pyrrole aldehyde, that is, this product is actually formed by the Wills-Mayer-Hack formylation of Pyrrole, and this aldehyde on reduction gives lithium aluminium hydride to the corresponding alcohol. So, if we look at the reaction of Pyrrole with the carbonyl compounds, especially formaldehyde in the presence of an acid, we again end up with the corresponding alcohols. The primary alcohol is formed. So, there are 2 ways by which we can prepare the carbenols from the Pyrrole. One is from the Wills-Mayer-Hack formulation followed by lithium aluminium hydride reduction gives the corresponding primary alcohol, or Pyrrole can be reacted with formaldehyde and the obtained intermediate is converted to the corresponding primary alcohol. So, these are all the 2 reactions by which the primary alcohol can be prepared. And there is also another important reaction which is a Mannich reaction. So, here the formaldehyde in the presence of a secondary amine gives the Mannich product as shown here. So, the mechanism is shown here. To proceed at 2 position, the first attack actually takes place, and the loss of proton leads to the aromatic Pyrrole derivative. And Pyrrole can be converted to porphyrin, similar to the reaction. As we have seen, the addition of the formaldehyde, multiple formaldehyde actually leads to the porphyrin derivative. And when we have this system, there is no extended aromaticity, but in this particular system we have a extended aromaticity, that is 18 pi electron system. So, this reaction very readily occurs. And when we look at the reactions of thiophene, thiophene undergoes sulfonation, chlorination and nitration. These are all the examples of electrophilic substitution reaction. That is the reason we can say thiophene. Of course, when we talk about the reactivity of thiophene, thiophene reacts much slower compared to furan and Pyrrole, and that is the reason if you look at the sulfonation reaction, in the case of furan and Pyrrole, we actually use pyridine and sulfur dioxide, which is comparatively milder reagent compared to sulfuric acid. So, in this particular case, thiophene does not undergo sulfonation that readily. So, that is the reason we have to use a strong reagent. So, sulfuric acid is used, and similarly nitric acid in the presence of acetic anhydride gives the 2-nitro derivative, and chlorine in the presence of light or SO2Cl2 gives the 2-chloro derivative. So, these are all the various reactions by which the electrophilic substitution of thiophene can be carried out. And Friedel-Crafts acylation is also possible on thiophene, because this is also an aromatic system like benzene. So, treatment with SnCl4 and acetyl chloride gives the 2 acylated product. Similarly, Wills-Mayer-Hack formulation gives the 2-formyl derivative of thiophene. So, these are some of the reactions, electrophilic reactions of thiophene. Of course, we can look at some of the applications of furan, thiophene and Pyrrole. So, here we will look at some of the examples of furan as a drug. So, furan nitrofuranatonin is a compound. This is used to treat urinary tract infection, and here we have the furan moiety that is present in this particular drug, and furosemide is also another drug which can be used to reduce the high blood pressure edema. It's a diuretics. Here again we have the furan ring present here, and cefuroxime is to treat infections like bronchitis, Lyme disease, etc. This is a cephalosporin antibiotic. This also has a furan ring. So, these are some of the important drugs that have the furan ring. And similarly, when we look at Pyrrole, tolmetin is a non-steroidal anti-inflammatory drug. So, this has a Pyrrole moiety, and this is used primarily to reduce the hormones that cause pain, swelling and tenderness. And we also have Alder. So, here this is a neotropic drug. This is used to treat Alzheimer's disease. This is also having a Pyrrole ring as shown here. And a very important drug, that is Lipitor. The commercial name is the Lipitor, which is Atorvastatin calcium. This is one of the best selling drug ever, with $125 billion sales over close to 15 years. So, the main unit that is present in this particular drug is the central Pyrrole moiety. So, this is mainly used to reduce the cholesterol, and this is a penta substituted Pyrrole derivative. So, this is a very unique drug, and this side chain is important for its HGMR inhibition. That is, this is generally used, this is a key enzyme in the regulation of cholesterol synthesis. So, use of this particular drug actually helps production of this particular enzyme in a much better quantities. So, if you look at the thiophene based drug, we have Pyrrole. This is having a thiophene unit, and this is used for treatment of parasitic worm infections. And ketotifen is another one. This is an antihistamine drug which is generally used for the treatment of eye, and this treated basically the allergic symptoms by blocking the certain natural substances like histamine. Let us recap in the summary what we have studied so far. We have studied about the various electrophilic substitution reactions of 5-membered heterocycles. We compared how the resonance energy and the reactivity are related with respect to benzene and other heterocycles we have seen. We also studied the various electrophilic substitution reactions of furan, thiophene and Pyrrole. We also studied the specific reactions, especially for furan, which is quite different from the normal electrophilic substitution. That is how a Diels-Alder reaction is happening, and we also studied about formation of non-aromatic product from furan. So, these are all the two unique reactions of furan. We have studied how these reactions are actually happening. So, the first is the electrophilic attack, followed by the nucleophilic attack when we talk about a non-aromatic product formation. We also studied about the reactions of Pyrrole and whether Pyrrole is an acid or a base we have seen. We also seen about the various reactivity and regioselectivity obtained for different substituted Pyrroles, especially N substituted Pyrroles. We also studied about a Mannich reaction, and we finally studied about the various electrophilic substitution reactions of thiophene. Thiophene, having a very high resonance energy compared to furan and Pyrrole, undergoes electrophilic substitutions much slower, but it is having lower resonance energy than benzene. So, it undergoes the reactions little bit better than benzene. So, these are all the things we have seen, and we also studied about some of the drug compounds containing 5-membered heterocycle. With that, we conclude this session. Thank you.